What is the link between C++ segmentation faults and memory protection? Imagine your program is like a busy city with different neighborhoods. Each neighborhood has its own set of rules about who can go where. If someone tries to enter a restricted area, alarms go off. That's what happens with segmentation faults in C++ programs. They are directly connected to how the operating system and hardware protect memory. In C++, memory is divided into sections called segments. These include the code segment where the program instructions live, the data segment for static variables, the stack for function calls and local variables, and the heap for dynamic memory. Each segment has rules about who can read or write there. Memory protection makes sure a program only accesses its own designated areas. When a program tries to access memory outside its boundaries, the hardware detects this illegal move. For example, if you try to dereference a null pointer or access an array beyond its size, you are breaking the rules. The hardware then triggers a segmentation fault. This signals the operating system to stop the program immediately to prevent damage or security issues. A segmentation fault often happens because of mistakes like dereferencing uninitialized pointers, which point to invalid memory, or when you write past the end of an array, overwriting other data. Using pointers after freeing memory is another common cause. Excessive recursion can cause the stack to overflow, leading to a segmentation fault. Buffer overflows, where data spills over into adjacent memory, also cause these faults. When a segmentation fault occurs, the operating system creates a core dump. This is like a snapshot of the program's memory at the moment of failure. Developers can analyze this dump to find out exactly where the illegal access happened. To debug these issues, programmers need to understand how memory protection works. Managing pointers carefully is key. Always initialize pointers before use. Check array indices to stay within bounds. After freeing memory, set pointers to null to avoid use after free errors. Tools like debuggers and memory checkers can help spot illegal memory access. For example, using a debugger like GDB or a tool like Valgrind can reveal where your program is trying to access forbidden memory. Understanding the link between segmentation faults and memory protection helps you write safer code. It shows you where your program might go wrong and how to prevent it. Recognizing these patterns makes debugging faster and easier. In C++ programming, respecting memory boundaries and using debugging tools effectively are your best strategies to fix segmentation faults and keep your program running smoothly.